Okay, Bismillah ar-Rahman ar-Rahim. So we're still talking about multi-axis techniques. So in the previous two lectures, we have talked about the Aloha protocol, and the Aloha protocol has the feature of ultimate freedom. So anyone in the meeting can talk at any point of time, and if there is any collision, we can resolve the collision. And we have seen that this, in terms of performance, which we have measured using the throughput, is the lowest, especially when the network load is high, and this because of the high probability of collision. Then we have introduced some restrictions by the slotted Aloha. We said that if the nodes can send freely, but at certain points of time, this will reduce the collision. And then we have talked about the SISMA or carrier sense multiple access, which introduces more restrictions. And by introducing these more restrictions and making the freedom more controlled or more regulated, then we can improve the system performance and we can enhance the throughput quite a bit. We have also talked about two cases for SISMA. We talked about the case when we can detect collision, in which case we will be proactive. We can respond to the collision right away, in which case we can save some time. And for the case of SISMA CA of collision avoidance, which is valid in the case of wireless. And we have talked about the different issues related to that. So today we'll start another category of multi-axis techniques, which are the controlled axis. In controlled axis, we want to eliminate collision altogether. And as we said, the only way for us to do that is by introducing another arbitrator or a controller or an access point that can moderate or can control the access to the medium. By doing this, we can have the control in the hands of one person or one node, and this node can dictate who can send when and in what sequence and everything. So logically speaking, if we talk about the logical topology of the network in that case, we have an arbitrator or a controller or a coordinator in the middle, and you have the nodes, around it. Okay, and the only way for us to have the control in the hands of this arbitrator is to force everyone to send and receive from the arbitrator. Okay, so anyone who wants to send anything, he or she should send it first to the coordinator, and then the coordinator can send it to others. So this is the only way that we can keep the control in the hands of the arbitrator. So we call the communication between the node and the arbitrator. We call this upstream communication. And for if the arbitrator wants to send to the node, we call this downstream communication. Okay, so nodes sending to the arbitrator is upstream, arbitrator sending to the nodes is downstream. So in this category of techniques, we have actually three, but I actually eliminated the third one, which is token passing. So we will cover only two techniques in that category. In both of these techniques, collision is totally eliminated, and we have a coordinator that controls the whole thing, controls who can access the medium at what time. Okay. So the first technique in this is reservation. And by reservation here, we mean that the only way to eliminate collision is by dividing the system into two phases. The first phase here, we call it a reservation phase. Okay, a reservation phase. And then this phase is called the transmission phase. So during the reservation phase, the nodes will not access the medium. The node will only declare their willingness to send or receive data. Okay, and by sending a control byte or a control signal to the arbitrator to say that, okay, so I have some data to send, or I'm willing to receive data from the arbitrator. To again, so we are sending only one byte, but we also need to make sure that when we send these bytes, we will not send the byte at the exact same time. So in order for this to happen, we have to divide the reservation phase into very, very small mini slots. We call this mini slots. These many slots will have as many slots as the number of nodes in the system. So here, clearly, we have 5 nodes in the system. So here we have to divide this reservation phase into very, very tiny, small slots, and each node can send its willingness to send or receive data. So here in this example, so here clearly node 1 is interested to send or receive. Node 2 doesn't have anything to send or receive. Node 3 is willing to send or receive data, and so on. Okay? So once this reservation phase is done at this point of time, here, at this point exactly, the arbitrator has complete knowledge of who is willing to send or receive data. Okay? So in which case, the arbitrator will broadcast a control a control message that has the sequence of who should send first and who should send second and who should send third, and so on. So if we see here that here node 1 and node 3 and node 4 are willing to send data, or they have some data to send, the arbitrator will say here, okay, so I will allow station 1 to send first for a certain duration of time, and then number 3, and then number 4. Okay, so if we organize it this way, then we eliminate collision, because we will never have a situation that 2 stations are sending at the same time. So the main advantage of this technique is that, of course, collision is eliminated completely by having the arbitrator work in this certain mechanism. So what is the disadvantage? The disadvantage here is, of course, we have slight overhead. So the reservation phase here introduces extra overhead, because we did not have to worry about this in the previous techniques. Whenever we have data to send, we just send. Here, we have to have this reservation phase, right? But this will give control to the arbitrator to have full control. So the arbitrator can then allow station 3 to send before station 1, or allow station 4 to send twice, or allow station 3 to send 3 times. So the arbitrator here will have full control, okay, to organize the access to the medium in any way it is appropriate. So it can provide some priority schemes if it wants. It can provide reordering to the transmission gate. It can give priority to some nodes over the other, and so on. Okay, so that's the reservation access method briefly. Another technique, which is called polling, it works slightly differently. So here we are talking about the 2 cases where we have here the downstream. This is the downstream phase, and this is the upstream phase. Okay, so for the downstream, what happens is that for the downstream, the communication goes from the primary node or from the arbitrator to one of the nodes. And remember here, in terms of physical topology, we could have a shared medium, or we could have a wireless medium. So in terms of physical topology, these nodes, they share the medium together. So when we talked about the logical topology and we said that everyone sends to the primary node, this is in terms of logical topology. But the physical topology, all the nodes, they share the same medium, whether it's wired or wireless. Okay? So for the case of downstream, so what will happen is that the primary node, for the case of polling mechanism, what it does is that to send one data to one of the nodes, it has to send first a select message. This select message, again, is a control byte, similar to the many slots that we talked about in the reservation phase. So in this select message, I will identify the node that I want to send this data to, which in that case is node B. Of course, this select byte will be sent over the shared medium, and all the nodes will be able to listen to it, but only B will see its physical address in this select message, and then it says, okay, acknowledge. This acknowledge means that I am willing to receive data from you at this point. Okay, so select and then acknowledge, and then the primary node will send the actual data, okay, which means that during that time nobody else should actually send anything over the line, which means that we will have no collision because everyone listened to the select statement or the select message from the primary node, and everyone listened to the acknowledge coming from node B. So by listening to these two messages, nobody should send anything over the line, right? Because only the primary node gives or grants the access to the medium to one specific node. Then when we send the data to node B should send acknowledgement. So why is this acknowledgement happening here? Because, I mean, someone might say, okay, so why do we need acknowledgement since we don't have any probability of collision here? But this acknowledgement is still important because this data might still get corrupted, in which case B will not receive the data correctly. So just the fact that there is no collision, it doesn't mean that there is 100% possibility that this data will be received successfully and correctly by node B. So in that case, node B should still send an acknowledgement to acknowledge the fact that the data has arrived successfully and correctly. واضح يا شباب؟ So this is for the case of downstream. For the case of upstream, the communication goes from the nodes to the primary node, from any node to the primary node. So of course, the primary node should have control. So the primary node should initiate who should have access to the medium. But the primary node doesn't know who has data and who does not have data. Okay? So the only way to do this, or the only way to organize this, is by sending a poll message. Poll message is to ask, Muhammad, do you have data to send? He says no. Amr, do you have data to send? He says no. Daniel, do you have data to send? Yes. So if Daniel has data to send, then Daniel will send the data right away, okay? And the primary node will send the acknowledgement, okay? So the only way for the primary node to know who has data and who has not is by sending a polling message, okay? So of course, here the overhead in terms of control messages from the primary nodes, to any of the nodes, is significantly higher compared to the reservation phase. Because here, for one data frame to be sent from the primary node to one of the nodes, we have 3 control messages. These 3 control messages have the purpose of eliminating collision and giving the control to the primary node all the time. واضح كده يا شباب؟ So we need to have 3 control messages in order to send one data frame. Of course, these control messages are like 1 byte, okay? And in the assignment 2, you will be able to calculate the overhead in terms of control messages for specific number of bits that I want to send from the primary node to the nodes in the upstream or downstream phase. Of course, in the upstream phase, it could be even more because the pull message, I could send multiple messages and the answer is no, I don't have data to send. Pull, no, pull, no, pull, no. I may have to do this several times with no data to be sent from the nodes to the primary node. Okay, but this is the only way for the primary node to know which of these nodes has data to send. واضح كده يا شباب؟ So these are the 2 techniques that we can have a primary node or arbitrator or a controller or a coordinator, which can be represented in practice as an access point, okay, or a base station in cellular networks or whatever. So in that case, this primary node is the main controller of the system, and everyone should send or receive data from that primary node. And that's the way to eliminate collision. Any question in that part about these two techniques? All right, so in the third category, as we have discussed before, the question is, we in order to eliminate collision completely, we had to introduce that primary node. So can we eliminate collision without having the primary node? And the answer is yes. But as we will see, we will have to برضو incur some overhead. So the only way to eliminate collision and still and have no arbitrator or no coordinator is by using the channelization. And by channelization, we mean that we will have a presetting of the system, okay, to follow one of these three possible ways. And we will organize this before we start communication, okay? So everyone will either use TDMA or FDMA or CDMA. Of course, the third one is totally new to you and you have not been introduced to CDMA before, but we will talk about it. So, in other words, we will come to the meeting with a preset configuration. Okay? Amr will talk first, then Muhammad, then Daniel, then Ibrahim, and so on. Okay? So each one will have a time slot. Each one will have a time slot, which is TDMA in that case. Okay? So if during my time slot I don't have data to send, then my time slot is wasted. But nobody else can use my time slot. Okay? Because again, we don't have any arbitrator or a primary node to organize such a thing. So the only way is to pre-configure the system. Okay? Or in other words, to divide the channel resources, to divide the shared medium resources, either in the time domain, or in the frequency domain, or in the code domain. And this is what we will talk about. Okay? So in that case, we have no primary node, no arbitrator whatsoever, and we have no collision. So that seems like a good advantage. But let's see the overhead of this. So the first technique that we will talk about in this category is what we call the frequency division multiple axis. Frequency division multiple axis talks about the fact that we will allow multiple nodes. Here we have 4 nodes, okay, to share the medium, okay, by dividing the medium into frequency bands. We talked about this before, that's not new, right? So each node will be assigned a frequency to transmit in that particular frequency range, right? So here, this is the frequency and this is the time. So we will divide the frequency. So in other words, let's say that we have a full spectrum for the whole system, like for example, 400 megahertz. So we'll say, okay, so we have 4 nodes, so each node will take 100 megahertz, okay? And the first 100 megahertz will be assigned to station 1, the second will be assigned to station 2, the third is station 3, and so on. So that's neat. So this is well organized, right? But the advantage of this is that, of course, we have no collision, we have no primary node, right? We have no arbitrator, no single point of failure. So everything is pre-configured to use frequencies, right? So let's see about the disadvantages. The disadvantage is that, for example, node 3 here is silent, which means that node 3 does not have any data to send. What will happen to this frequency range? It's wasted. It's not utilized in any way, right? So all these frequency bands is currently not utilized in any way. So that's a waste, right? This is a waste, but this is the only way for us to have no collision with no primary node, right? So in the previous category, the existence of the primary node minimizes the overhead because we don't have to allocate resources to a node and the node does not have any data to send, right? We don't have to allocate a long duration of time and the data does not have any data to send. The node does not have any data to send, right? So in terms of disadvantage, the first thing is that if a node is not having data to send, this frequency band will be wasted, right? So that's not good. The other thing is that, of course, if a node wants to receive data from node 1 or node 2 or node 3, what does this node need to do? Let's say node 5. We have node 5 here, and node 5 wants to receive data from node 1, right? So this node 5 needs to apply a filter on this frequency band, right? But the problem is that, of course, these filters are not ideal. These filters are not like this, right? So here we need to have, so these filters are like this, in which case we need to have a guard band. So first thing is that we need to have here like guard bands between the between these frequency ranges. These guard bands account for the fact that at the receiver side, I have to use a realistic filter which has some damping effect, and this damping effect requires the fact that these guard bands should be significant in order to minimize the interference between the transmitted data from 1 and the transmitted data from 2 and so on. واضح كده يا شباب؟ So these guard bands are one of the overheads that I have to incur or I have to pay. Of course, remember here that node 5 as a receiver, node 5 is the receiver now. Node 5 should apply a filter, okay, to each of the bands that it wants to receive data from, which means that the transceiver or the receiver at node 5 needs to be able to receive from multiple frequencies. Okay, so each node sends to one frequency, but the receiver should be able to receive from multiple frequencies, because node 5 needs to sometimes receive data from node 1, or receive data from node 2, or receive data from node 3, in which case it needs to have multi-frequency reception. واضح كده؟ So the transmission is separate, but the reception has to happen, for each one individually, which means I need to support all frequencies, which of course slightly increases the complexity of the receiver, right? So that's the first part in terms of advantages and disadvantages. Another way, so here we will divide the full bandwidth into separate frequency ranges equal to the number of the nodes, okay? And we should have guard bands between each frequency range. In the time division multiple axis, we will divide the system not by in the frequency domain, but in the time domain, in which case we will come to the meeting with a preset configuration that node 1 will talk first, then node 2, then node 3, then node 4, and so on. So similar to the frequency division multiple axis, the number of time slots, okay, is equal to the number of the nodes, and of course these time slots will recycle. So this is node 1, 2, 3, 4, and then node 1, 2, 3, 4, and then node 1, 2, 3, 4, and it goes in that order all the time. Okay. So again, if node 3 does not have any data to send, this means that this time slot here is wasted. Okay, it's allocated, and the shared medium is not used in that particular time slot, which is, again, it's a waste. Another disadvantage is, again, here the guard band. برضو here we have guard bands. These guard bands actually are designed for two things. Okay, we talked about the first one, which is that whenever we have multiple nodes, each one with a clock, then we will have a clock drift, then we will have the issue of synchronization, right? So synchronizing these nodes, okay, in the time domain, and the nodes are distributed, then in that case we will have an issue. So in order to account for the clock drift, we should have guard bands. So the guard bands has two functions. One is to account or to account for synchronization or lack of synchronization between the nodes. Two, actually the guard bands are needed because of the propagation delay. So remember here that these nodes, they share a median. Okay? So when a node sends a signal, okay, this signal propagates to the end of the line, and this propagation delay, right, is somewhat significant. During that time, all the other nodes should be able to listen, but they cannot send anything over the line. So this guard band also accounts for the propagation delay. Okay? So the guard bands in the case of TDMA accounts for two things, right? The lack of synchronization between the nodes or the clock drift, يعني, and the propagation delay. Okay, كده? So again, in that case, the advantage is that no primary node, no collision whatsoever. So everything is organized, but we will have to have these guard bands between the nodes to account for the lack of synchronization and the propagation delay. Okay, واضح كده يا شباب؟ So the third type here is So this is for TDMA. We of course we divide the channel into time slots, and time slots will be separated by the guard bands. Number 3 بقى, which is called code division multiple access. Okay, and I need you to focus here because this is completely new to you. Code division multiple access, by the way, is the predominant technology or the predominant modulation scheme for all 3G cellular communication. Okay, all 3G cellular communication, they use CDMA, code division multiple access. Okay, of course, now we have 4G and 5G, and these they use even more advanced technology that came after CDMA, which we will not cover as part of this course. Type, what is the idea of CDMA? As we said that if you have two nodes or two person, let's say two people, okay. This is person number 1, person number 2, person number 3, person number 4. What we said is that if these two they communicate together, and these two they communicate together, and this communication happens at the same time, at the same frequency, then there is collision. صح? What we said is that if Amr is talking to Muhammad, okay, and Ali is talking to Ibrahim, okay, and these two conversations are happening at the exact same time, at the exact same frequency, then if anyone in the back of the room here, someone is here in the back of the room, he wants to listen to this communication or to this communication, this person will not be able to distinguish the two conversations happening together, right? That's what we refer to as collision. Okay? Just imagine that these two communications are happening like this. Amr is talking to Muhammad using Chinese. Okay? Ali is talking to Ibrahim using English. And the reason for Chinese and English is that these two languages are totally uncorrelated. They have no relationship whatsoever. They use different dialects, they use different phonetics, they use different letters, they use different directions, they use totally different things. Okay, so if this person or the receiver, if that person understands Chinese, okay, and he's trying to listen to the two conversations, okay, if we imagine that scenario, we can say that this person will be able to extract Chinese from the two languages easily, right? Right? So if that person understands English, again, he should be able to distinguish English from the composite conversations that's happening. Okay? So this is the main idea of CDMA, is that before the conversation happens, okay, so before the conversation between Amr and Muhammad happens, I will code this conversation in Chinese, okay, and the other language, and sorry, the other communication, I will code it in a language that's totally orthogonal or totally uncorrelated to the first language, okay, so that if one person wants to extract the Chinese from the composite conversation, he should be able to do that easily. Okay, so that's the main idea of CDMA. It's a very simple idea, but it was actually revolutionary at the time, and it was the predominant technology, as I said, for the 3G. So how does this happen? So in reality, what happens is that Node 1 wants to send data D1. Node 2 wants to send data D2. Node 3 wants to send data D3, and Node 4 wants to send data D4. So before transmitting D1, I will code it with a code. So this is what we call CDMA code for station 1. Okay, so this is, for example, Chinese. Okay, so I will code D1 in Chinese. I will code D2 in Persian. I will code D3 in English. I will code D4 in Arabic. Okay, and so on. These languages, they are totally uncorrelated. So for this, of course, when all of them, they send at the same time, at the same frequency, the shared medium will have this composite signal. The composite signal is in fact D1 multiplied by C1 plus D2 multiplied by C2 plus D3 multiplied by C3 plus D4 multiplied by C4. Okay? So this is the composite signal on the line. So anybody can listen to this composite signal, right? But in order for me to receive data from station 1, I need D1 from this composite signal. Okay? Or I need D2 from this composite signal. So how do I do this? In order for you to do that correctly, we have two very, very important conditions on these codes. Okay? So these codes, they should have these two extremely important conditions. One, any CI multiplied by CI, okay, which means that the code is multiplied by itself in terms of dot product, and I will show you now what this dot product means. Okay, the answer should be n, such as n is the number of stations. In that case, it's 4. Okay, which means that any code should have high correlation with itself. The code has high correlation with itself. Okay, so this is the first condition. Condition number 2 is that when I do the same dot product between Ci and Cj such that I does not equal j, the answer is always 0. Always. Okay, should always be 0, which means that this condition means that the codes are orthogonal. Okay? Codes are orthogonal means that they do not have mutual correlation with each other. They are not correlated with each other. One is Chinese, one is English. They are totally disseparate from each other. واضح كده؟ So this means that the code has high correlation with itself. Okay? And I will let you know what is the condition for this to happen. And if I multiply any two codes, okay, such as I is not equal to j, the answer is always 0. So let's apply this. So let's see. Let's imagine that node 5 or any node, it wants to send. It wants to receive data from node 2, which means that node 5 is interested to receive D2, right? So for this to happen, node 5 needs to have C2. If you want to receive Chinese, you should understand Chinese, right? So that's basic. So in that case, node 5 will multiply C2 times the composite signal. Okay? So if I multiply C2 times the composite signal, so let's see, this will lead to D1 multiplied by C1 multiplied by C2. What is the answer here? C1 multiplied by C2 is a 0, right? So, and then D2 multiplied by C2 multiplied by C2, which will lead to D2 multiplied by N, right? Which means that D2 will be amplified. D2 will be amplified. And then D3 multiplied by C3 multiplied by C2 is also 0. Multiplied by C4 is also 0. So this will lead to all the terms will be 0 except for the one that I want to receive data from, which is in that case D2. So the result of this will be D2 multiplied by N. Okay? Which means that all the other languages will vanish and the Chinese language will be amplified. Right? So that's the idea. That's the simple idea. Right? So this is like a numerical example. So let's imagine that we have these codes. Sometimes we call them CDMA codes or CDMA chips. Okay, these are the two names are for the same thing. So these are the chips or the codes. So let's apply the two conditions that we talked about on this numerical example. Okay, so for example, C1, the first condition is that C1 should have high correlation with itself, which means that if I multiply C1 by C1, which means 1, 1, 1, 1, and the dot product is easily, I multiply 1 times 1, right? Plus 1 times 1, plus 1 times 1, plus 1 times 1. So the answer is 4. Okay? Same thing here. If I'm talking about C2, so this is 1 minus 1, 1 minus 1. So again, if I multiply C2 by itself, the answer is 4. And here is 4. And here is 4. So this is condition 1. Condition 2 talks about that if I multiply C1 by any of the other nodes, any of the other codes, okay? Which means C1 multiplied by C2, so the answer is 1 minus 1, 1 minus 1. So the answer is 0. Okay? Apply for C1 by C3. Okay? So 1, 1, and then minus 1, minus 1. So the answer is 0. C1 by C4, same thing, 0. And this will be the case for all the other codes. So if you take any of these two codes and multiply the code by any other code, the answer is always 0. So what is the idea behind this, ya shabab? So why is 4 And how can I maintain this to be 4? The only thing to maintain this to be 4, which means that the code will have high correlation with itself, is to eliminate the use of zeros. If you use 0, why do we use 1 and minus 1 here? Because 1 times 1 is 1. Minus 1 times minus 1 is 1, right? But we cannot use 0. Why? Because 0 times 0 is 0. So if you multiply the code by itself, the answer will be less than 4. Okay? So the only best thing we need to keep in mind is that the codes have to always be bipolar, or in other words, either use 1 or minus 1, but you never use 0. Similarly, we will talk about the data. So even the data now, we cannot use 1 and 0. We have to use 1 and minus 1, which means that we will have to map the 0, okay, in the data to minus 1 in the digital signal. And we know how to do this. We have used bipolar schemes before. So for the 1, we use positive voltage. For the 0, we use negative voltage, right? So that's easy. So we should always use 1 and minus 1 in the codes, and we should never use 0 in order to maintain this high correlation with itself, that C1 times C1 is always 4, C2 times C2 is always 4, and so on. واضح كده? All right? So, and of course, any two codes are orthogonal to each other, which means that the dot product of each two codes is always 0. Okay? طيب, applying this بقى to the data representation. So as we said, before transmission, we need to map the bit 1 يعني, if you have a stream of 0 1 0 1 0 1 and so on. Okay? So we will map this one to positive voltage or 1. The 0 should be mapped to minus 1. Okay? And again, this is done to maintain the high correlation of the code with itself. Okay? That because minus 1 times minus 1 is 1. Okay? And 1 times 1 is 1. But the 0 times 0 is 0. So the only scenario where we use 0 is when the node is silent, and I will show you this in a minute. Okay? So if a node has any data, 0 or 1, we map the 0 to minus 1, we map the 1 to the 1, عادي. If a node does not have any data to send, we map this to the 0, which means that the node is silent. Okay? This again to a numerical example. So node 1 or station 1 wants to send 0. Okay? So as we said, we will map this 0 to minus 1. So node 1 now wants to send minus 1. Minus 1 يعني minus voltage يعني. Okay? And this is the code assigned to station 1. Okay? And these codes, of course, are organized in such a way that they fulfill the two conditions we have talked about. The code has high correlation with itself, and the code is orthogonal to all the other codes. Okay? So if node 1 wants to send 0 or minus 1, I will multiply this minus 1 by the code. Okay? So I will have multiplying a number by this code will lead to a vector. So multiplying minus 1 by 1, 1, 1, 1 will lead to minus 1, minus 1, minus 1, minus 1. Okay? Node 2 wants to send again 0, which means minus 1. I multiply this by the code, which is 1 minus 1, 1 minus 1. So the answer is minus 1, 1, minus 1, 1. سهل كده? I think this is very easy. Okay? Node 3 is silent. Okay? Which means that node 3 is not contributing anything to the composite signal. So I will map this to 0. 0 times anything is 0. So this 0 vector will not add anything to the shared or composite signal on the shared medium. Okay? So station 4 will have bit 1, which is positive 1. So positive 1 multiplied by the code, which will lead to the same code, which is 1 minus 1, 1 minus 1. So all these nodes or all these stations, remember, they are sending this data at the same time, at the same frequency. So what you will get on the line, is actually the summation of all these vectors, D1 times C1, D2 times C2, D4 times C4. Okay? So the addition of these is a vector which looks like this. So -1, -1, and 1. So the answer here is -1. -1, 1, and then -1. The answer here is -1. And then -1, -1, -1. The answer here is -3, and so on. Very easy. So this is the composite signal, which corresponds to C1, D1 times C1 plus D2 times C2 plus D4 times C4. Okay. So this is the vector that will represent the composite signal, and this vector will go through the shared medium. Okay. Everybody will be able to listen to this composite signal. If a node 5 or any node wants to receive data from node 2, it should have C2. If it wants to receive data from node 1, it should have C1. If it wants to receive data from C4, it should have C4. Which means essentially is that, again, the receiver should have all the codes from all the nodes that it wants to communicate with. Right? Similar to, as we said, similar to in the frequency division multiple axis, we said that, again, we should have a filter at every single frequency that we want to receive data from. Same here. So we want to have the codes for all the nodes that we want to communicate with. Okay? واضح so far? So that's the numerical example. So let's see in terms of digital signals, because all of these, remember, all of these are simply digital signals. Okay? These digital signals, by the way, when they are sent using either baseband communication or broadband communication, again, this composite signal, it gets impacted by noise, distortion, and attenuation, everything. Okay? So in terms of digital signal, wants to send data 0, right? The signal looks like this. So station 1 will have data 0, which is -1, of course. And when we multiply this by the code, it leads to this digital signal, which is -1 all the way. Node 2 will have this digital signal. Node 3 will have this. Node 4, sorry, will have this. Node 3, of course, is silent, so nothing. Okay? And then we will add this on top of each other. So this is the composite signal that we will receive. Of course, what's not accounted for here is that this composite signal will have to be transmitted over the digital medium, which means that we can introduce to it, again, attenuation, distortion, all types of noise, and so on and so forth. Right? So if a node, that's correct. So station 2, if a node, any node, in that particular example, we have node 3 wants to receive data from station 2 or node 2, right? So in order for node 3 to receive data from station 2, node 3 should have C2, and C2 is 1 minus 1, 1 minus 1, right? It multiplies this signal by the composite signal. It multiplies the code by the composite signal. So 1 multiplied by -1 is -1. -1 multiplied by -1 is 1. And then -3 multiplied by 1 is -3. And then 1 multiplied by -1, so the answer is -1. Right? If we add this, if we add all of this, -1 plus 1 is 0. And then we have -3 and -1. So the answer is -4. Okay? And -4, if we divide it by 4, the answer is -1. And -1, as we know, it maps to 0. So this means that station 2 is in fact trying to send data 0. And that's so At the receiver side, what we typically do is that we use actually a voltage integrator. We use a voltage integrator. So what happens is that the summation happens through accumulation. So I have a digital signal of -1, so the accumulator will say, oh, okay, so I will have to go to -1. And then I will have 1, which means that I will go back to 0, right? And then I will have -3, which means I will go to -3, and then I will have 1, which means I will go to -4. Then this -4 will be used against a voltage comparator. If it's below 0, then it's the original data is 0. If it's above 0, the original data was 1. So in that case, it's clearly 0. Why do we use accumulator like this or an integrator like this? Because remember, again, in practice, this digital signal is not idealistic like this. So there is attenuation, so there is an effect of noise, okay, that might happen to the signal. So we typically use integrators to accumulate all the signal values up to here. And of course, the value here may be a 3.7, -3.7, or maybe -4.1, something like that, right? So it's not as ideal as -4. So of course, the example here is idealistic, but in practice, we should have like some attenuation, some noise effect, distortion, things like that. So the accumulator will result to maybe -4.1 or -3.8. But of course, as we said, because of the fact that the data from station 2 will be multiplied by n, because the code has high correlation with itself, so it's as if the signal from station 2 is actually amplified. And that's very good because the effect of noise is even so this is against the effect of noise. So even if we have some noise on the signal, the fact that we amplify the signal from station 2 compensates for any noise that we might have, right? Okay, so any question so far? So this is the idea. So the question here is that so these codes seems to be magical then, because I mean, how can we have codes that fulfill these two conditions systematically? So in a system, we want to be able to generate these chips. We call them chips or codes. Okay, so we want to generate these chips or codes in a systematic way, right? So and as the system grows large, we need to be able to also generate these codes, right, in such a way that fulfills these two conditions. So the question is, do we have a systematic way of doing that? And the answer by Walsh is that yes, we have this. Okay. The only small, tiny little issue here is that the Walsh method of generating these chips or these orthogonal codes should go in a multiple of 2. Okay? So Walsh created a matrix, okay, which has all the rows of this matrix will always fulfill the two conditions we talked about. Okay? So any Walsh matrix, okay, will have the rows of these matrix fulfilling the two conditions we talked about. So the only basic glitch here, or the only issue, is that Walsh matrix will have a dimension which is always in the power of 2, which means that we cannot have a Walsh matrix of 5 times 5. We cannot have a Walsh matrix of 9 times 9. We can never have this. Okay? Either 1 by 1, or 2 by 2, or 4 by 4, or 8 by 8, or 16 by 16, or 32 by 32, and so on. Okay? Type. If we agree on this small issue, what is the systematic way? The systematic is very, very simple. If we start with a Walsh matrix of 1 by 1, okay, then I can generate the Walsh matrix of 2 by 2 by simply replicating the 1 in a triangle like this. So 1, 1, 1, and then minus 1. Okay? Which means that recursively, the Walsh matrix of dimension double the one before it is by simply replicating the Walsh matrix in a triangular way like this, and the other one will be the toggle. The fourth one will be the toggle, which means that you multiply it by minus 1. Very, very simple. Very simple. Okay? So if you do it like this, very simply, if you have any two rows, Wn multiplied by Wn, okay, is Wn, and Wn multiplied by minus Wn is minus Wn, and if you get the summation, the answer is always 0. So this will fulfill the orthogonality condition, And by the fact that we use here 1 and minus 1, the condition 1 is also achieved, which means that any row will have very high correlation with itself. C1 multiplied by C1 is n, C2 multiplied by C2 is n, and so on. واضح كده? Okay, so we always have to go in a power of 2. Walsh matrix has to be generated in a power of 2. So this is how it looks like. So always we have n equals to 2 to the power m, right? So if we want to generate for 2 stations, then we have Walsh of dimension 1 by 1 is 1. Okay, so Walsh 2 is in fact 1, 1, and 1 and minus 1. Okay, so we'll take this, we repeat it in a triangular way like this, and the fourth one will be the toggle. If we want to generate Walsh 4, we take Walsh 2, we replicate it, so it becomes 1, 1, 1, minus 1. 1, 1, 1, minus 1. 1, 1, 1, minus 1, and then we toggle. The other one will be minus 1, minus 1, minus 1, 1. Okay, so this is for Walsh 4. Walsh 8, we will take all these 4 by 4 matrix and replicate it 3 times, and the fourth one will be multiplied by minus 1. So if we have 4 stations, we will take each row of this matrix and assign it to each node. So here we have 4 stations, will be assigned to these 4 codes or 4 vectors, and all these codes are orthogonal to each other by default. Okay? So the idea is that in typical systems, I cannot force the system to have a number of nodes, power of 2. Yani I cannot have a typical system of that has to have either 32 nodes or 64 nodes. I always have somewhere in between. So what is the solution for this? And like the solution is easy. Yani if we have 90 stations, okay, in our network, then we cannot generate a Walsh matrix of 90 by 90. صح? We cannot have 90 by 90. Why? Because 90 cannot be 2 of power integer number. 90 cannot be 2 of power integer number. So we have to go to a 128. We have to go. So 2 to the power 6 will give you 64. So 64 is not enough. So we have to go to 2 to the power 7, which is 128. Okay? So what do? I will generate a Walsh matrix of 128. Okay? I will take the first 90 vectors, the first 90 rows, and I will assign them to the 90 stations. And the other 38 vectors, I will keep them for future use. Okay? That's easy. Okay? So I can always use subset of these vectors. But the problem with Walsh matrix is that you can never generate a Walsh matrix of a number which is not power of 2. Okay? Okay? So any question, ya shabab? So So this is the proof that we talked about. So a proof that the receiving station can get data sent by a specific sender if it multiplies the entire data on the channel by the sender chip code. So if I want to receive, for example, the data from station 2, right? So all I need is, if I want, here is station 1, let's say. If I want to receive data from station 1, I should multiply this composite signal by C1, right? So the answer is, if I multiply the composite signal by C1, so this will lead to a multiplying all these terms by C1, okay? And this will lead to D1 multiplied by C1 multiplied by C1. So this will lead to D1N, and all the other terms will be 0, which means that station 1 data will be amplified, and all the other data from all the other stations will be eliminated. So this, similar to the example of a node wants to receive the Chinese language from a composite, multi-language conversation. So in that case, I can do that easily if I understand only Chinese. ماشي? Any questions so far, Shabab? So that's the end of this chapter. Again, very quickly, in this chapter we have arranged the multi-access techniques into 3 different categories. The first category is the contention-based access. In contention-based access, we do not eliminate collision. We have to deal with it. And we have talked about a different elaboration or a different evolution of techniques. We went from the ultimate freedom, which is the pure Aloha, okay, and then we introduced some restrictions, and by introducing some restrictions on how the nodes are accessing the channels, we have been able to improve the performance of the system slightly. So we introduced the slotted Aloha, and then we introduced the SYSMA, or carrier sense multiple access, okay, and we have shown that with more restrictions or with more regulations on the freedom of the nodes, we can reduce collision, but we can never eliminate it. So the only way we eliminate it is by having a primary node or a coordinator or an arbitrator. So the second category of techniques talks about the controlled access, where collision is totally eliminated by having a primary node. And in that category, we talked about 2 techniques. The reservation access. Reservation-based access talks about the fact that the communication will be divided into 2 phases. The reservation phase is divided into many slots, and the nodes can send their willingness to send or receive data during these many slots. And then the transmission phase will be arranged easily by the primary node by controlling the sequence or the duration of transmission for each node. The other technique is the polling technique, by having the primary node polling the nodes whether they have data to send or not. Okay? And then the third category of techniques, which we call channelization, where we eliminate collision and have no primary node or no arbitrator at the same time, which is very attractive. But as we said, this will come with a cost that you assign or you divide the channel resources between the nodes before you start communication, but of course, this will lead to some resources that are wasted by having a frequency range that's not utilized by the node, or having a time slot that's not utilized by the node. Then we introduced the CDMA, which is the predominant communication scheme for third generation wireless networks, where we can code the signals or the data from the multiple nodes using orthogonal codes. Okay? Any questions, ya Shabab, in this chapter? طيب. We will start quickly the last part, or the dynamic routing protocol. We'll just give a light introduction, and then we'll continue next time, inshallah. So in terms of dynamic routing protocols, of course, in network 1, we have talked about IP protocol, and we have talked about routing table, where we use the routing table to route data from one local network to a remote network. So as we said before, the best way to understand routing is to imagine yourself going from your home مثلا to QU, and while going from home to QU, you need to take a specific route or a specific commute. And in every intersection, you should have a router, or you should have a person that tells you whether to go left or right or straight or something like this, right? And this should lead to the fact that you go to QU in the shortest way possible. And this shortest way is relative. So shortest, as we said before, could be, determined or could be estimated by the number of streets that you have to go through, or how loaded this street is, the width of the street, or something like this. So similarly in networks, the best route is actually calculated based on different matrix, and we talked about the concept of matrix. So here in this course, we will focus on dynamic routing protocols. Dynamic routing protocols are actually the protocols that they exchange, or they facilitate the exchange of messages between the routers in order for each router to fill the routing table, right? So, of course, we talked about, very lightly, we talked about two categories of routing protocols. There is the static routing protocol, and there is the dynamic routing protocols. We talked about these two. In static routing, the network analyst will update the routing table manually, right? Dynamic routing protocols, they support automatic exchange of routing data between the routers, and that's the main focus of this part. So in this course, we will focus on dynamic routing protocols, how these messages, they will get exchanged between the routers, how do routers use these messages to update the routing tables, right? So the dynamic routing protocols, they have three major functionalities. We have the routers, they dynamically share information between the routers. So as we have discussed before, each router knows exactly what's physically connected to it. So router 1, for example, has some LANs and has some point-to-point connections to all the other two routers. Okay. At the beginning, when router 1 starts, it knows exactly all the links and all the LANs that are directly connected to it. And we have talked about this in network 1. So once the router 1 starts the interfaces, it should feel from the physical layer that you have LAN 1 and you have LAN 2 and you have point-to-point link 1, point-to-point link 2. Okay? So router 1 will collect information about all these links, and then it will send it in a message. It will compose an update message, okay, which will have information about these links and these LANs. And then it will send this message to the other two routers. Okay. Router 3 will do the same. Router 2 will do the same. Okay. And all the routers, they will receive multiple messages from all other routers, right? So this is what will happen in step number 1, or the first function. Number two is that routers, they will collect all these messages and they will automatically update the routing table when topology changes, right? So for example, if node 1 loses LAN 2, which means that this link is disconnected, this is a topology change. So router 1 will update the message here and will send it to router 2 and router 3. Router 2 and router 3, they should automatically detect that there is a topology change, okay, and update the routing table accordingly with the best path. So for example, today you are going from your house to QU, right? You took a certain commute. Tomorrow, what will happen, especially, mashallah, in Qatar, we have new roads that open every day, right? So all of a sudden, from your house, you found that there is a new bridge or a new highway or a new road that has, existed that did not exist before. You should get triggered and you should try to utilize that road, because it may actually lead to the best path from your house to QU, right? So these two steps are very important because they require some intelligence. Okay, so exchanging messages is easy, it's systematic, but to conclude that from these messages there is a topology change and there is a new best path that you need to update your routing table with, that requires some intelligence, right? So that happens through an algorithm. So exchanging messages is easy, but how to use these messages requires some brain, requires some intelligence, and that's what we refer to as routing algorithm. Routing algorithm, right? So with that said, the dynamic routing protocols can be divided into two major components. There is the routing algorithm. The routing algorithm is the brain of the system. This is the one that interprets the messages, and based on which it detects, there is now a topology change. There is a new best path that I have to use, okay, other than the one in the routing table that did not exist before, right? And of course, component 2, which is responsible for exchanging the routing protocol messages, right? So these are the two components and the functionalities of the dynamic routing protocols. Okay. Of course, the other technique or the other category of techniques, which is the static routing. And as we said before, static routing is based on the fact that there is no intelligence. There is a tedious process that a network analyst, okay, has to go through all the routers in the system and log on to each router, okay, and be able to fill the routing table on each router, in which case he should have the topology in his head. He should have all the best routes, everything in his head, okay, and he should manually set up the routing table. Of course, the advantage of static routing is that it's easy. I don't have to have sophistication and exchanging messages between the routers. I don't have to have extra resources by messages going back and forth and have an algorithm, a sophisticated algorithm to take this message on. And it's secure because as we said before, any protocol that has broadcast messages, okay, is subject to attacks, because I can always say, okay, so I can impersonate myself as a router and I can send you wrong information, and I tell you here is a route update, and this route update contains wrong information about the topology of the system, and if you embed this message in the routing table, this will lead to routing loops, and this will lead to a wrong routing table, and the routing tables will not become consistent in that case. If I rely on one person to do all this job, of course, this is more secure, because assuming that this person is not the hacker, of course, this person will log on to every single router and will update the routing tables. But the disadvantage here is that, of course, when there is any slight change in the system, this person has to re-log on to every single router and has to apply all these changes. And of course, this will not lead to scalability, because imagine if I have like 100 routers or 1,000 routers, static routing will not be feasible in any way. So static routing is only valid for small topology and for fixed network. Okay? So static routing will be useful if I have a very small network. Sometimes we only use static routing for the default gateway, which connects me to Ooredoo, for example. Okay? So only to configure the gateway that will take the traffic to Ooredoo, I can use static routing in that case, because this will possibly not change much, and it's a very, very small network. So in that case, static routing is going to be useful. Okay, Shabab? So this is a very quick introduction, and inshallah next time we will talk about the different categorization of these dynamic routing protocols and how can we use the different matrix to characterize these dynamic routing protocols.